Properties of acids and bases. Acids and bases play a central role in much of chemistry that affects your daily life. Your body needs acids and bases to function properly. Vinegar, carbonated drinks, and foods such as citrus fruits contain acids. The electrolyte in a car battery is an acid. Most manufacturing processes use acids or bases. Bases are present in many commercial products including antacids and household cleaning agents. Figure 19.1 shows some of the many products that contain acids and bases. Acids have several distinct properties with which you are probably familiar. Acidic compounds give foods a tart taste or sour taste. For example, vinegar imparts a tart taste to salad dressings. Figure 1, many items contain acids or bases or produce acids and bases when dissolved in water. Citrus fruit contain citric acid. Tea contains tannic acid. Antacids are used to neutralize excess stomach acid. And D, the base calcium hydroxide or quicklime, is a component of mortar. Vinegar contains ethanoic acid, sometimes called acetic acid. Lemons, which taste sour enough to make your mouth pucker, contain citric acid. Aqueous solutions of acids are electrolytes. Recall from the chapter on water and aqueous systems that electrolytes conduct electricity. Some acid solutions are strong electrolytes and others are weak electrolytes. Acids cause certain chemical dyes called indicators to change color. Many metals, such as zinc and magnesium, react with aqueous solutions of acid to produce hydrogen gas. Acids react with compounds containing hydroxide ions to form water and a salt. Acids taste sour, will change the color of an acid-base indicator, and can be strong or weak electrolytes in aqueous solutions. Here is an example of how a Lewis base and Lewis acid reacts. The Lewis base is the electron donor, and the electron acceptor is the acid. Bases have properties with which you are less familiar. Bases have a bitter taste, but tasting most bases is hazardous. Soap is a familiar material that has the properties of a base. If you have tasted soap, you know that it has a bitter taste. The slippery feel of soap is another property of bases. Like acids, aqueous solutions of bases are electrolytes and will cause an indicator to change color. Water and a salt are formed when a base that contains hydroxide ions reacts with an acid. With a few exceptions, none of the foods you eat are bases. Milk of magnesia, a suspension of magnesium hydroxide in water, is a base used to treat the problems of excess stomach acid. Bases taste bitter, feel slippery, will change the color of an acid-base indicator, and can be strong or weak electrolytes in aqueous solutions. Arrhenius acids and bases. Although chemists have recognized the properties of acids and bases for many years, they were not able to propose a theory to explain this behavior. Then, in 1887, the Swedish chemist Svante Arrhenius proposed a revolutionary way of defining and thinking about acids and bases. Arrhenius said that acids are hydrogen-containing compounds that ionize to yield hydrogen ions in aqueous solutions. He also said that bases are compounds that ionize to yield hydroxide ions in aqueous solutions. Arrhenius acids. Table 1 lists some common acids. Acids that contain one ionizable hydrogen such as nitric acid, are called monoprotic acids. Acids that contain two ionizable hydrogens are called sulfuric acids, such as sulfuric acids, are called diprotic acids. Acids that contain three ionizable hydrogens, such as phosphoric acid, are called triprotic acids. Not all compounds that contain hydrogen are acids, however. Also, not all the hydrogens in an acid may be released as hydrogen ions, such as methane, etc. Here are some of the more common acids found: hydrochloric acid, nitric acid, sulfuric acid, phosphoric acid, ethanoic acid, such as acetic acid, and carbonic acid. Only the hydrogens in very polar bonds are ionizable. In such bonds, hydrogen is joined to a very electronegative element. When a compound that contains such bonds dissolves in water, it releases hydrogen ions because the hydrogen ions are stabilized by solvation. An example is the hydrogen chloride molecule shown in Figure 2. Hydrogen chloride is a polar covalent molecule. It ionizes to form aqueous solution of hydronium ions and chloride ions. Here is a picture, kind of a blown up picture of Figure 2, and it details the formation of the hydronium ion. Notice the charge differential in the hydrogen chloride in the upper left, where you have the slight positive, and partial negative atoms that make up the hydrogen chloride. Acid names and uses. Acids can often be purchased at hardware and home supply stores, but they are often labeled with odd names. For example, muriatic acid is no longer used in chemistry. It's hydrochloric acid. Among other uses, this acid is purchased to clean lime deposits from tile and porcelain, and to clean mortar stains from brick and tile. In contrast, the four hydrogens in methane are attached by weakly polar CH bonds. Methane has no ionizable hydrogens and is not an acid. Ethanoic acid, CH3COOH, used in the manufacture of plastics, pharmaceuticals, and photographic chemicals, is different. Although this molecule contains four hydrogens, ethanoic acid is a monoprotic acid. The structural formula shows you why. The three hydrogens attached to the carbon are in weakly polar bonds. They do not ionize. Only the hydrogen bonded to the highly electronegative oxygen can be ionized. As you gain more experience looking at written formulas for acids, you will be able to recognize which hydrogen atoms can be ionized. Arrhenius bases, Table 2, lists some common bases. The base with which you are perhaps most familiar is sodium hydroxide, called Li. Sodium hydroxide is commonly known as Li. Sodium hydroxide is an ionic solid. It dissociates into sodium ions and hydroxide ions in aqueous solution. And there's the formula. NOH yields Na plus and OH negative. Because of its extremely caustic nature, sodium hydroxide is a major component of consumer products used to clean clogged drains and can cause severe burns if not used properly. Potassium hydroxide, KOH, is another ionic solid that dissociates to form potassium ions and hydroxide ions in aqueous solution. Sodium and potassium are group 1A elements. The elements in group 1A are just one, universally. The alkali metals react with water to produce solutions that are basic. Sodium metal reacts violently with water to form sodium hydroxide and hydrogen gas. Very, very caustic, very dangerous, to be treated with great care. The following equation illustrates the reaction of sodium metal with water. 2Na plus 2HOH yields 2NaOH plus 1H2, or hydrogen molecule. Sodium hydroxide and potassium hydroxide are very soluble in water. Concentrated solutions of these compounds can be readily prepared. Such solutions, like other basic solutions, would have a bitter taste and slippery feel. However, they are extremely caustic to the skin and can cause deep, painful, slow-healing wounds if not immediately washed off. Calcium hydroxide and magnesium hydroxide are compounds of group 2A metals, or just group 2. These compounds are not very soluble in water. Their solutions are always very dilute, even when saturated. The concentration of hydroxide ions in such solutions is correspondingly low. A saturated solution of calcium hydroxide contains only 0.165 grams of calcium hydroxide per each 100 grams of water. Figure 3, milk of magnesia is a base used in an antacid, and we'll see why that's true later on. Bases are usually hazardous when taken internally, but the low solubility of milk of magnesia makes it much more safe. Magnesium hydroxide is much less soluble than calcium hydroxide. A saturated solution contains only 0.00009 grams magnesium hydroxide per 100 grams of water. Suspensions of magnesium hydroxide in water contain low concentration of hydroxide ion. People take these suspensions internally as milk of magnesia, shown in Figure 3, which is an antacid and a mild laxative. Bronsted-Lowry acids and bases. The Arrhenius definition of acids and bases is not a very comprehensive one. It defines acids and bases rather narrowly and does not include certain substances that have acidic or basic properties. For example, aqueous solutions of sodium carbonate, Na2CO3, aqueous, and ammonia, NH3, are basic. Neither of these compounds is a hydroxide, however, and neither would be classified as a base under the Arrhenius definition. In 1923, the Dutch chemist Johann Bronsted and the English chemist Thomas Lowry independently proposed a new definition. The Bronsted-Lowry definition, or theory, defines an acid as a hydrogen ion donor and a base as a hydrogen ion acceptor. All the acids and bases included in the Arrhenius theory are also acids and bases according to the Bronsted-Lowry theory. Some compounds not included in the Arrhenius theory are classified as bases in the Bronsted-Lowry theory. And the same will be true in the Lewis theory of acids and bases. Why ammonia is a base? The behavior of ammonia as a base can be understood using the Bronsted-Lowry theory. Ammonia gas is very soluble in water. When ammonia dissolves in water, it acts as a base because it accepts a hydrogen ion from water. And you can see the equation there. And that's what actually makes it a base, because it's producing hydroxide. And just to be clear, it does not have hydroxide in its formula, but causes the production of hydroxide, so it produces it indirectly. But because it's producing the hydroxide, it is considered a base. In this reaction, ammonia is the hydrogen ion acceptor and therefore is a Bronsted-Lowry base. Water, the hydrogen ion donor, is a Bronsted-Lowry acid. Hydrogen ions are transferred from water to ammonia, as is shown in figure 5, which is the next slide. This causes the hydrogen ion concentration to be greater than it is in pure water. As a result, solutions of ammonia are basic. Figure 4 here shows sodium carbonate decahydrate, and that it is used as a laundry aid. Its common name is washing soda, and it is a base, and the reason it's a base is because the salt of a weak acid, when ionized, will produce hydroxide and be a base. Here is the reaction of ammonia and water. You see the formation of the ammonium ion, and it takes one of the hydrogens, and what's left is the hydroxide. Now, it's a weak base, but nevertheless it is a base and will produce excess hydroxide ions free in solution. And you see the base and the corresponding conjugate acid and the corresponding conjugate base. Because all gases become less soluble in water as temperature increases, increasing the temperature of an aqueous solution of ammonia releases ammonia gas. As ammonia gas leaves the solution, the equilibrium in the equation shifts to the left. The ammonium ion reacts with hydroxide to form NH3 and H2O. When the reaction goes from right to left, ammonium gives up a hydrogen ion. It acts as a Bronsted-Lowry acid. The hydroxide ion accepts an H+. It acts as a Bronsted-Lowry base. Overall, then, this equilibrium has two acids and two bases. When ammonia dissolves and then reacts with water, NH4+ is the conjugate acid of the base, NH3, or ammonia. Here is a picture of what an acid looks like when it's donating a proton to a base. Proton donor acid, proton acceptor base, and then the corresponding conjugate acid and conjugate base. A conjugate acid is the particle formed when a base gains a hydrogen ion. Similarly, hydroxide is the conjugate base of the acid water. A conjugate base is the particle that remains when an acid has donated a hydrogen ion. Conjugate acids and bases are always paired with a base or an acid, respectively. A conjugate acid-base pair consists of two substances related by the loss or gain of a single hydrogen ion. The ammonia molecule and ammonium ion are a conjugate acid-base pair. The water molecule and hydroxide ion are also a conjugate acid-base pair. And there is the equation below relative to ammonia and ammonium. The Bronsted-Lowry theory also applies to acids. Consider the dissociation of hydrogen chloride in water, where you produce hydronium and chloride, respectively. In this reaction, hydrogen chloride is the hydrogen ion donor. Thus, it is a Bronsted-Lowry acid. Water is the hydrogen ion acceptor, and therefore water is a Bronsted-Lowry base. A water molecule that gains a hydrogen ion becomes a positively charged hydronium ion, H3O, plus 1 charge. I recommend you drawing the molecular geometry structure to see what the structure is of the ammonium ion. You'll see that it is trigonal pyramidal. Here is the reaction where you have clearly listed the conjugate acid and conjugate base from the hydrogen chloride and water, and it is a molecular geometry is I tried to show a little bit there. So where you're looking kind of down on it, the chloride ion is the conjugate base of the acid HCl. The hydronium ion is the conjugate acid of the base water. Figure 6 shows the reaction that occurs when sulfuric acid dissolves in water. That's sulfuric acid dissolving in water, and you're producing the hydronium ion and the hydrogen sulfate ion, HSO4, -1 charge. And there's a better shot of it, and you see the conjugate acid and base pairs, and a little bit about the geometry of the sulfuric acid molecule, very clearly drawn there. And it gives you a little bit of an idea of what's going on. You can see those hydrogens are kind of hanging out on either side of the molecule that are easily hydrolyzed from water. The solution formed consists of hydronium ions and hydrogen sulfate ions. Sometimes water accepts a hydrogen ion. At other times it donates a hydrogen ion. A substance that can act both as an acid and a base is said to be amphoteric. Water is amphoteric. In the reaction with HCl, water accepts a proton and is therefore a base. Amphoteric comes from the Greek word amphoteros, meaning partly one, partly the other. An amphoteric substance can act as both an acid and a base. What makes an amphibious airplane different from other airplanes? Here's a table which shows the conjugate acid-base pairs of a variety of acids and how to recognize them and the corresponding base. A third theory of acids and bases was proposed by Gilbert Lewis. Lewis proposed that an acid accepts a pair of electrons during a reaction, while a base donates a pair of electrons. This concept is more general than either the Arrhenius theory or the Bronsted-Lowry theory. A Lewis acid is a substance that can accept a pair of electrons to form a covalent bond. A Lewis base is a substance that can donate a pair of electrons to form a covalent bond. A hydrogen ion, Bronsted-Lowry acid, can accept a pair of electrons in forming a bond. A hydrogen ion, therefore, is also a Lewis acid. So you're getting away from the whole concept of hydrogen being involved at all, as you'll see later on. So a Bronsted-Lowry base, or substance that accepts a hydrogen ion, must have a pair of electrons available and therefore is also a Lewis base. Consider the reaction of H plus and OH minus. In this reaction, a hydroxide ion is a Lewis base. It is also a Bronsted-Lowry base. The hydrogen ion is both a Lewis acid and a Bronsted-Lowry acid. Here is a summary of that slide, where you have the hydrogen ion is accepting a pair of electrons, and the hydroxide is donating them. So this would mean that the hydrogen ion, being an electron acceptor, is the acid, and the hydroxide, which is donating them, is the base. Ammonia dissolved in water is another example of a Lewis acid and Lewis base. In this reaction, the hydrogen ion from the dissociation of water is an electron-pair acceptor and is a Lewis acid. Ammonia is an electron-pair donor and is a Lewis base. Below are the acid-base definitions for Arrhenius, Bronsted-Lowry, and Lewis theories of acid-base analysis, and the table will summarize that. Here is an example where you have ammonia is going to be the electron donor and boron trifluoride will be the electron acceptor. So the boron trifluoride in this case is an acid and the ammonia is a base. Not particularly what you would think of as being an acid and a base, but it is consistent with acid-base theories based on Lewis and his analysis. As you already know, water molecules are highly polar and are in continuous motion even at room temperature. Occasionally, the collisions between water molecules are energetic enough to transfer a hydrogen ion from one water molecule to the other. A water molecule that loses a hydrogen ion becomes negatively charged hydroxide ion. A water molecule that gains a hydrogen ion becomes a positively charged hydronium ion, H3O+. The reaction in which water molecules produce ions is called the self-ionization of water. This reaction can be written as a simple dissociation, where water is on the left, H2O, and on the right is H+ and OH-. In water or aqueous solution, hydrogen ions are always joined to water molecules as hydronium ions. Hydrogen ions in aqueous solution have several names. Some chemists call them protons. Others prefer to call them hydrogen ions or hydronium ions. In this textbook, either H+ or H3O+ is used to represent hydrogen ions in an aqueous solution. Figure 7 shows how two water molecules react to form one hydrogen ion and one hydroxide ion. So this is a summary of that reaction. The self-ionization of water occurs to a very small extent. In pure water at 25 degrees Celsius, the equilibrium concentration of hydrogen ions and the equilibrium concentration of hydroxide ions are each only 1 × 10⁻⁷. This means that the concentration of the H+ and OH- are equal in pure water. Any aqueous solution in which H+ and OH- are equal is described as a neutral solution. Very, very important. Ion product constant for water. In any aqueous solution, when H+ increases, OH- decreases. When H+ decreases, OH- increases. Le Chatelier's principle, which you learned about in Chapter 18, applies here. If additional ions, either hydrogen ions or hydroxide ions, are added to a solution, the equilibrium shifts. The concentration of the other type of ion decreases. More water molecules are formed in the process. Now look at the equilibrium equation below. That's where we're going to get the ionization equation from, that equation for water. Very, very, very important. For aqueous solutions, the product of the hydrogen ion concentration and the hydroxide ion concentration equals 1 × 10⁻⁴. That's because they're both equal. When you multiply like bases, you add the exponent. So -7 plus -7 is -14. This equation is true for all dilute aqueous solutions at 25 degrees Celsius. As you will see, the concentration of H and OH may change when substances are added to water. However, the product of the molar concentration of the H+ and the molar concentration of the OH- is always 1 × 10⁻⁴. The product of the concentrations of the hydrogen ion and hydroxide ions in water is called the ion product constant for water, or Kw, and that equation is there, and Kw is going to be 1 times 10 to the negative 14. Very important. Notice that the H plus and the OH minus are molar concentrations. Not all solutions are neutral. When some substances dissolve in water, they release hydrogen ions. For example, when hydrogen chloride dissolves in water, it forms hydrochloric acid, as shown here. In such a solution, the hydrogen ion concentration is greater than the hydroxide ion concentration. The hydroxide ions are present from the self-ionization of water. An acidic solution is one in which H plus is greater than OH minus. An acidic solution is one in which the H plus is greater than the OH minus. The H plus of an acidic solution is greater than 1 times 10 to the negative 7th. So it's going to be greater, but a greater exponent. So negative 6 would be acidic, negative 7 would be neutral, given those parameters, as well as negative 8, negative 9, negative 10 would mean that it would be a basic solution. When sodium hydroxide dissolves in water, it forms hydroxide ions in solution, as shown here. In such a solution, the hydrogen ion concentration is less than the hydroxide ion concentrations. Remember, the hydrogen ions are present from the self-ionization of water. A basic solution is one in which the H plus is less than the OH. The H plus of a basic solution is less than 1 times 10 to the negative 7th molar. Basic solutions are also known as alkaline solutions. Some uses for acids and bases are shown in Figure 8. Figure 8, acids and bases have many uses in the home and in industry. Unrefined hydrochloric acid, commonly known as muriatic acid, is used to clean stone buildings and swimming pools. Sodium hydroxide, or lye, is commonly used as a drain cleaner. The pH concept. Expressing hydrogen ion concentration in molarity is cumbersome. A more widely used system for expressing H ion concentration is the pH scale, proposed in 1909 by the Danish scientist Sorensen. On the pH scale, which ranges from 0 to 14, neutral solutions have a pH of 7. A pH of 0 is strongly acidic, one that is completely dissociated. The solution with a pH of 14 is strongly basic. Calculating pH, the pH of a solution is the negative logarithm of the hydrogen ion concentration. The pH may be represented mathematically using the following equation. pH equals the negative log of the H ion concentration. And pOH would also be similar to that relative to the negative log of the OH ion concentration. In a neutral solution, the H plus equals 1 times 10 to the negative 7th. The pH of a neutral solution is 7. You can calculate the pH of a solution using the log function key on a calculator. Ions in water. Explain to the students that all aqueous systems contain both hydrogen and hydroxide ions due to self-ionization of water. At 25 degrees Celsius, about 1 molecule of water out of 550 million will dissociate. This amounts to 1 gram of hydrogen ions and 17 grams of hydroxide ions in 10,000 liters of water. No matter how small the concentration, both ions are always present in a water solution. The relationship between the concentration of H plus and OH minus in aqueous solutions at constant temperature is similar to the relationship between the pressure and volume of a gas at constant temperature. In both cases, the relationship is inverse. The product of the two quantities is a constant. As one quantity increases, the other decreases. Figure 9 shows how the hydrogen ion concentration of a solution is used to classify the solution as neutral, acidic, or basic. The solution in which H plus is greater than 1 times 10 to the negative 7th molar, has a pH less than 7, and is acidic. The pH of pure water or a neutral aqueous solution is 7. The solution with a pH greater than 7 is basic and has a H plus ion concentration of less than 1 times 10 to the negative 7th. So on the pH scale, acidic solutions, pH less than 7, the H ion concentration is greater than 1 times 10 to the negative 7th. Neutral solutions, it's equal to 1 times 10 to the negative 7th. And basic solutions is less than 1 times 10 to the negative 7th. So we will see how indicators can tell you what the general range is of the pH. Here's figure 9, and it shows the relative concentrations of the ions, hydroxide and hydronium, in acidic, basic, and neutral solutions. The pH values of several common aqueous solutions are listed in Table 5. The table also summarizes the relationship among H plus and OH minus and pH. You may notice that pH can sometimes be read from the value of H plus ions. If the H plus ion is written in scientific notation and has a coefficient of 1, then the pH of the solution equals the exponent, with the sign changed from minus to plus. For example, a solution of 1 times 10 to the negative 2 of the H ion concentration has a pH of 2, and a solution with H plus of 1 times 10 to the negative 13 has a pH of 13. If the pH is an integer number, it is also possible to directly write the value of H plus ion concentration. A solution of pH 9 has a H ion concentration equal to 1 times 10 to the negative 9th molar. A pH of 4 indicates the molar concentration of the H ion concentration to be 1 times 10 to the negative 4 molar. And here is Table 5 as promised, with various items and the corresponding pH of those items. For instance, pure water is 7, blood is between 7 and 8. Blood is basic. The pOH of a solution equals the negative logarithm of the hydroxide ion concentration. The formula is listed there. A neutral solution has a pOH of 7. A solution with a pOH less than 7 is basic. A solution with a pOH greater than 7 is acidic. A simple relationship between pH and pOH allows you to find either one when the other is known. When you have the pH plus the pOH equal to 14. So you can calculate the pOH by saying 14 minus the pH, and you can calculate the pH by saying that it's going to be 14 minus the pOH. pH and significant figures. For pH calculations, you should express the hydrogen ion concentration in scientific notation. For example, a hydrogen ion concentration of 0.0010 molar, rewritten as 1 times 10 to the negative 3 molar in scientific notation, has two significant figures. The pH of the solution is 3.00, with the two numbers to the right of the decimal point representing the two significant figures in the concentration. A solution with a pH of 3.00 is acidic, as shown in figure 10. Most pH values are not whole numbers. For example, milk of magnesia has a pH of 10.5. Using the definition of pH, this means that the H ion concentration must be equal to 1 times 10 to the negative 10.5. Here is figure 10 and the pH scale from 0 to 14. Notice the increasing acidity from 7 to 0 and the increasing basicity going from 7 to 14 and the corresponding H ion concentrations. Thus, the H ion concentration, the molar concentration, must be less than 1 times 10 to the negative 10th, pH of 10, but greater than 1 times 10 to the negative 11th molar, or pH of 11. If H ion concentration is written in scientific notation, but its coefficient is not 1, then you use a calculator with a log function key to calculate pH. You can calculate the hydrogen ion concentration of a solution if you know the pH. For example, if the solution has a pH of 3, then the H ion molar concentration is equal to 1 times 10 to the negative 3 molar. When the pH is not a whole number, you will need to calculate with a 10 to the x function key to calculate the hydrogen ion concentration. For example, if the pH is 3.70, the hydrogen ion concentration is greater than 1 times 10 to the negative 4 molar, or a pH of 4, and less than 1 times 10 to the negative 3 molar, a pH of 3. To get an accurate value, use a calculator as shown in the following example, which is actually not here, but in the textbook. People need to be able to measure the pH of the solution they use, from maintaining the correct acid-base balance in a swimming pool to creating soil conditions ideal for plant growth, to making medical diagnoses. pH measurements have valuable applications. For preliminary pH measurements and for small volume samples, an indicator such as the one shown in figure 11 is often used. For precise and continuous measurements, a pH meter is preferred. Figure 11, acid-base indicators respond to pH changes over a specific range. Phenolphthalein, pronounced phenolphthalein, changes from colorless to pink at pH 7 to 9. Later on I'll be showing you a table with a variety of indicators with a variety of ranges. Here again is another illustration that shows pH and corresponding substances that have individual pHs. For each indicator, the change from dominating acid form to dominating base form occurs in a narrow range of approximately 2 pH units. Within this range, the color of the solution is a mixture of the colors of the acid and base forms. Knowing the pH range over which this color change occurs can give you a rough estimate of the pH of the solution. At all pH values below this range, you would see only the color of the acid form. At all pH values above this range, you would see only the color of the base form. You could get a more precise estimate of the pH of the solution by repeating the experiment with indicators that have different pH ranges for their color changes. Many different indicators are needed to span the entire pH spectrum, and oftentimes these pH indicators are embedded onto paper, as well as individual solutions that can be titrated into the solution in question. Here are a variety of pHs and the corresponding indicators that might be used. Figure 12 shows the pH ranges of some commonly used indicators. Indicators have certain characteristics that limit their usefulness. The listed pH values of indicators are usually given at 25 degrees Celsius. At other temperatures, an indicator may change color at a different pH. If the solution being tested is not colorless, the color of the indicator may be distorted. Dissolved salts in a solution may also affect the indicator's dissociation. Using indicator strips can help overcome these problems. An indicator strip is a piece of paper or plastic impregnated with an indicator. That is one reason it's very important to use distilled, deionized water when making any kind of acid or base solution. Making it with clean glassware and clean water is very, very important. Here's another shot of that where we go from thymol blue, and you can see phenolphthalein down in the bottom, and each indicator measures approximately 1.5 to 2 pH units. The paper is dipped into an unknown solution and compared with a color chart to measure the pH. Some indicator paper is impregnated with multiple indicators. The colors that result, which cover a wide range of pH, are shown in Figure 13 on the following page. This works really well if you're trying to narrow down what a solution is, but if you're checking blood where a tenth of a change in pH could indicate some kind of illness or some kind of problem that you'll have, an indicator is not indicated for general use of this nature. You can find acidic and basic substances in your home. Universal indicator solution has been added to solutions of known pH in the range from 1 to 12 to produce a set of reference colors. Universal indicator has been added to samples of vinegar, soda water, and ammonia solution. And here is a color palette which can show you what the general range might be. Again, this does not work with tenth of a pH change. That would need a pH meter. Sodium, magnesium, milk of magnesia, magnesium hydroxide can be used as a laxative or as an antacid buffer solution for the stomach, which is hydrochloric acid. Also, here are some various types of bases that you'll use in the home. For instance, washing soda is basic. Washing soda is made of sodium carbonate, which is the salt of a weak acid, and the salt of a weak acid is basic and can actually lower the amount of hydrogen ion in solution. Now, talking about pH meters, let's talk about pH meters. A pH meter makes rapid, accurate pH measurements. Most chemistry laboratories have a pH meter. A pH meter connected to a computer or chart recorder can be used to make a continuous recording of pH changes. As you can see in Figure 15, the pH meter gives a direct readout of pH. A pH meter is often easier to use than liquid indicators or indicator strips. It is also more accurate. Measurements of pH obtained with a pH meter are typically accurate within 0.01 pH unit of the true pH. The color and cloudiness of the unknown solution, it does not affect the accuracy of the pH value obtained. As I said before, you can see 0.01. Very minor changes in blood chemistry can indicate something might be seriously amiss. This is Figure 15. It shows a pH meter, and it provides a quick and accurate way to measure the pH of a solution. For instance, A, water is neutral, having a pH of 7. B, the pH of vinegar, a dilute aqueous solution of ethanoic acetic acid, is approximately 2. It's actually, I think, a little greater than 2. It might be more like 3. The pH of milk of magnesia, an aqueous suspension of magnesium hydroxide, is 10.5. Hospitals use pH meters to find small but meaningful changes of pH in blood and other body fluids. Sewage, industrial effluents, and soil pH are also easily monitored using pH meters. Again, here's another pH scale with a range of pH going from 0, hydrochloric acid, to 14, sodium hydroxide. Figure 14 has 3 pictures, all of plants. Altering soil pH can affect the development of plants. A, in acidic soils, hydrangeas produce blue flowers. In basic soils, hydrangeas produce pink flowers. Evergreen plants, C, suffer from chlorosis a yellowing of foliage, D, if the soil is too basic. I had many evergreens in my yard back in the United States, and when I first moved into the house, there were a lot of calcium carbonate rocks, or rocks made of calcium carbonate, the white marble, and I got rid of them because they turn the soil basic, because calcium carbonate is the salt of a weak acid. Salts of a weak acid make the soil basic, and evergreens prefer acidic soil. So if you have evergreen plants in your yard, you don't want to put stones around your evergreens that are going to produce basic effluent from the calcium carbonate, and it will leach a little bit, not a lot, but you want to make sure that the soil is healthy and slightly acidic. Weak acids ionize only slightly in aqueous solution. The ionization of ethanoic acid, acetic acid, a typical weak acid, is not complete. However, this will be the setup for buffers and buffer systems, understanding this particular reaction and what this reaction actually leads to when you take the salt of a weak acid and introduce that as a buffer system. Table 6 shows the relative strength of some common acids and bases, such as hydrochloric acid, nitric acid, which are among the strongest acids, down to sodium hydroxide and potassium hydroxide, which are among some of the strongest bases. You can see that ammonia is a relatively weak base, as is ethanoic acid or acetic acid. Hypochlorous acid is a very weak acid and used as a buffer in buffer systems. Acid dissociation constant. In an aqueous solution of ethanoic acid, fewer than 1% of ethanoic acid molecules are ionized at any instant. Therefore, ethanoic acid is considered a weak acid. Figure 16 compares the extent of dissociation of strong, weak, and very weak acids. The strong acid completely dissociates in water as a result of the hydronium ion being high. Hydrochloric acid and sulfuric acid are examples of strong acids. On the other hand, weak acids such as boric acid and carbonic acid remain largely undissociated. The hydronium ion of a weak acid is low. You can write the equilibrium constant expression from the balanced chemical equation. The equilibrium constant expression for ethanoic acid is shown below. Very important expression. Very important. Figure 16 demonstrates and compares differences and similarities among strong acid, weak acid, and very weak acid. The interpreting graph section to the left of that diagram, A, explain in the graph for the strong acid why are the heights of the hydronium and anion bars the same as the height of the HA bar. B, inferring in the graph for the weak acid why is the height of the hydronium bar the same as the distance from the top of the second HA bar to the dotted line. And C, applying concepts, draw a bar graph for the dissociation of the weak diprotic acid, oxalic acid. Be sure to include the first and second dissociation. So let's examine what we would conclude from A, B, and C on the next slide. And also I included a molecular diagram of oxalic acid, which is a organic acid, essentially. It's very weak, but when you think of organic chemistry, you think of oxalic acid, and it's a weak acid again. And on the next page, we have the answers to the analysis. So A, where it says explain in the graph for the strong acid why are the heights of the hydronium ion and the anion bars the same as the height of the HA bar. Well, in the dissociation of an acid HA in water yields hydronium and the anion A, we'll call it. The bar graph compares the extent of dissociation of strong, weak, and very weak acids. Now, A, the strong acid dissociates completely, forming equal amounts of ions. B, where it says inferring in the graph for the weak acid, why is the height of the hydronium bar the same as the distance from the top of the second HA bar to the dotted line? The amount of the acid that dissociates is equal to the amount of the two resulting ions. And in C, apply concepts by draw a bar graph for the dissociation of a weak diprotic acid, oxalic acid. Be sure to include the first and second dissociations. We would say the bar graph for the first dissociation of oxalic acid should show low concentrations of the H plus and the oxalate. The bar graph for the second dissociation, that should be bioxalate, the bar graph for the second dissociation should show even lower concentrations of the H plus and the oxalate or the anion. Prospective students may note that the H plus in the second bar graph actually should be much higher than the oxalate or the anion without any hydrogens because of the H plus ions produced in the first dissociation. Just to go back and to make clear, when you lose one hydrogen off a diprotic acid, let's say the anion is acetate or oxalate, that's the anion, you would say that's the polyatomic ion would be oxalate or acetate. Well, if it's a diprotic acid and you have one hydrogen left over, you either call it hydrogen acetate, hydrogen oxalate, or you could call it, based on an old style, you would use bi for the presence of hydrogen, you would say biacetate, or bicarbonate, or bioxalate. So, in the human body, where you're using carbonic acid, when carbon dioxide is released from cell respiration, it goes into the blood as a buffer pair, as an acid, carbonic acid, and the conjugate base, bicarbonate or hydrogen carbonate. And so when you have a diprotic acid, and after the release of the first hydrogen, you call it hydrogen acetate or hydrogen oxalate in this particular case. And then the second dissociation, you would call it simply that polyatomic ion, either carbonate, oxalate, in this case oxalate, or acetate. For dilute solutions, the concentration of water is a constant. It can be combined with KEQ to give an acid dissociation constant. An acid dissociation constant, Ka, is the ratio of the concentration of the dissociated or ionized form of an acid to the concentration of the undissociated, non-ionized form. The dissociation form includes both the hydrogen ion concentration, hydronium ion, and the anion, and that's shown there. The acid dissociation constant, Ka, reflects the fraction of an acid in the ionized form. So you take the water out of it. And that's a little confusing to understand, but vital in understanding acid-base chemistry. For this reason, dissociation constants are sometimes called ionization constants. If the value of the dissociation constant is small, then the degree of dissociation or ionization of the acid in the solution is small. Weak acids have small Ka values. The stronger an acid is, The larger is its Ka value. A larger value of Ka means the dissociation or ionization of the acid is more complete. For example, nitrous acid has a Ka of 4 times 10 to the negative fourth, whereas ethanoic acid, acetic acid, has a Ka of 1.8 times 10 to the negative fifth. This means that nitrous acid is more ionized in solution than ethanoic acid. Nitrous acid is a stronger acid than ethanoic acid. Therefore, a strong acid has a higher hydronium ion concentration and a large dissociation constant. Conversely, a weak acid has a low hydrogen ion concentration and a small dissociation constant. Diprotic and triprotic acids lose their hydrogens one at a time. Each ionization reaction has a separate dissociation constant. Thus, phosphoric acid, H3PO4, has 3 dissociation constants to go with its 3 ionizable hydrogens. Table 7 shows the ionization reactions and dissociation constants of some common weak acids, ranked by the value of the first ionization constant of each acid. And what you'll find is that the acid, the first ionization energy is always the highest, and the third is always the lowest. And you can see with phosphoric acid, it goes 10 to the negative 3 down to 10 to the negative 13. Losing ions. Diprotic and triprotic acids lose their hydrogen ions one at a time. Each successive ion is more difficult to lose from the negative ion. Phosphoric acid loses one hydrogen ion relatively easily, leaving hydrogen dihydrogen phosphate ion. This negatively charged ion loses fewer hydrogen ions than phosphoric acid, and even fewer hydrogen ions, leaving biphosphate. Although phosphoric acid contains 3 acidic hydrogens, it does not have a high degree of ionization and is therefore a relatively weak acid. Just as there are strong acids and weak acids, there are also strong bases and weak bases. Strong bases dissociate completely into metal ions and hydroxide ions in aqueous solution. Some strong bases, such as calcium hydroxide and magnesium hydroxide, are not very soluble in water. The small amounts of these bases that do dissolve dissociate completely. Weak bases react with water to form the hydroxide ion and the conjugate acid of the base. Ammonia is an example of a weak base. Here is ammonia plus water yields the ammonium ion and the hydroxide ion. The equilibrium of this equation greatly favors the reverse reaction. Only about 1% of the ammonia is present in ammonium, the conjugate acid of NH3. The concentrations of ammonium and hydroxide are low and equal. The equilibrium constant expression for the reaction of ammonia with water is listed there. Notice the water is there as well, so that's going to be the KEQ. The concentration of water is constant in dilute solutions. It can be combined with KEQ to give a base dissociation constant, or a KB. You'll see how the waters cancel, and you're left with KB equals the product of the molar concentration of hydronium and hydroxide ion multiplied together, divided by the ammonium ion. In general, the base dissociation constant KB is the ratio of the concentration of the conjugate acid times the concentration of the hydroxide ion to the concentration of the base. The general form of this equation is as follows. So it's going to be the molar concentration of the conjugate acid times the molar concentration of the hydroxide divided by the molar concentration of the base. The magnitude of Kb indicates the ability of a weak base to compete with the very strong base, hydroxide, for hydrogen ions. Because bases such as ammonia are weak relative to the hydroxide ion, Kb for such bases is usually small. The Kb for ammonia is 1.8 times 10 to the negative fifth. The smaller the value of Kb, the weaker is the base. Figure 17, a solution of phosphoric acid is used to remove lime deposits from plumbing fixtures. Lime deposits are calcium carbonate, and that's generally from water. Water can have calcium carbonate that precipitates out onto the piping and can cause some difficulty for the person who's using those pipes, for instance, showers, etc. Figure 18, window cleaners use ammonia solution to clean glass because it is a weak base. Being a weak base also makes ammonia relatively safe to use. You'll note that bases are soapy, and that's one reason they work. So look at the structure of the soap molecule, the concept of the base, and what it's actually trying to dissolve. And if you look at the molecular geometry, things will make a little bit more sense to you. Something else that you might want to consider is, can a base act as a surfactant? Will it get rid of some of the hydrogen bonding that occurs in water? And what will that do to the grime on windows? Concentration and strength. The words concentrated and dilute indicate how much of an acid or base is dissolved in solution. These terms refer to the amount of moles of the acid or base in a given volume. The words strong and weak refer to the extent of ionization or dissociation of an acid or base. They indicate how many of the particles ionize or dissociate into ions. Hydrochloric acid is a strong acid. It is completely dissociated into ions. Gastric juice in the stomach is a dilute solution of hydrochloric acid. A relatively small number of HCl molecules are present in a given volume of gastric juice, but they are all dissociated into ions. If you have an acid stomach or heartburn in your chest or between your chest and your stomach, that's generally due to the hydrochloric acid. A sample of hydrochloric acid added to a large volume of water becomes more dilute, but it is still a strong acid. Vinegar is a dilute solution of a weak acid, ethanoic acid. Pure ethanoic acid, glacial acetic acid, is still a weak acid, even though it is highly concentrated. Solutions of ammonia can be dilute or concentrated depending on the amount of ammonia dissolved in a given volume of water. In any solution of ammonia, however, whether concentrated or dilute, ammonia will be a weak base because the amount of ionization will be small. Table 8 lists the concentration of acids and bases commonly found in the laboratory. In industry, you use enormous quantities of acids and bases on the order of billions of dollars. Here are some common acids and bases and their concentrated form. In other words, saturated form would be the concentrated form. And you'll see that in hydrochloric acid in the concentrated form or saturated form would be, you can fit 12 moles of hydrochloric acid in 1 liter of solution. Dilute hydrochloric acid, or 6 molar, which would be about half. Look at sulfuric acid, 18 moles. So you can fit 1.7 kilograms of sulfuric acid in 1 liter of solution. and that's 438, about a pound of hydrogen chloride gas in a liter of water. Look at dilute aqueous ammonia. You have 6 moles, which is quite a bit. You have dilute sodium hydroxide. Look at ethanoic glacial acetic acid, 17 moles compared to 6 moles in a liter for the dilute form of ethanoic or acetic acid. Calculating dissociation constants. You can calculate the acid dissociation constant Ka of a weak acid or the base dissociation constant Kb of a weak base from experimental data. To find the Ka of a weak acid or the Kb of a weak base, substitute the measured concentrations of all the substances present at equilibrium into the expression for Ka or Kb. For a weak acid, you can determine these concentrations experimentally if you know the initial molar concentration of the acid and the pH, the H ion concentration, of the solution at equilibrium. Now remember, the dissociation constant, the Ka or Kb, does not have water in it. The water times the KEQ equals the Ka or Kb, depending. In general, for an acid in water, you can find Ka by substituting the concentrations of the acid, Ha, the negative ions from the dissociation of the acid, the anion A, negative one, or whatever it is, and the hydrogen ion concentration into the equation below. Ka equals the molar concentration of the hydronium ion times the anion divided by the acid. As more is learned about the damaging effect of airborne pollutants such as acid rain, there is a growing concern to preserve historic buildings and pieces of sculpture from damage. Stone conservators work to prevent and repair the damage to stone used in buildings and sculptures. Stone conservators must clean statues properly to remove pollution deposits. One method they use is to apply a thin clay mud pack to the stone surface to pull out the deposits. Lasers are also used to remove pollution from stone when making repairs. Stone conservators sometimes use surgical microscopes to examine the surfaces of statues. You would think from this first slide that there would be maybe some acid or base used to clean, but the acids are so detrimental to anything with calcium carbonate in that it would destroy the stone that is being used for the sculpture or the buildings. Now these buildings are all around the world, anywhere there's stone. So you have stone buildings from, gosh, the Middle Ages that have to be taken care of. If the stone was originally painted, the original paint is chemically analyzed to determine its composition. In addition, conservators research and apply methods to preserve the stone once it has been repaired. One preservation technique is to seal the stone to prevent water, which carries dissolved gases and salts, from seeping into the pores of the stone. Stone conservators often work for museums, universities, or private companies that specialize in the cleaning and restoration of stone objects. They must have knowledge of both chemistry and art because they often work closely with both chemists and museum personnel. A stone conservative's level of education may range from a bachelor's degree to a doctorate, and it is in great demand, by the way. And they work on buildings all around the world, on sculptures, on old cathedrals, you name it, Roman ruins, whatever the case may be. So there's a lot to work with. Acids, bases, and curly hair. Curly hair from a permanent wave involves an acid-base neutralization reaction. The waving solution is basic and has a pH of about 20. The active ingredient in the waving solution is often an ammonium compound that is applied once the hair has been rolled. After a specified time, the hair is rinsed to remove the excess base. Then a neutralizer is applied. The neutralizer is an acid solution that has a pH of 2 to 6. If the hair is exposed to the waving solution for too long a period of time, the hair's texture and appearance are damaged. And you can see why women don't get, or men don't get waves put in their hair or perms put in their hair, because the acid in the base will actually destroy the hair and you'll be bald instead of having a nice hairdo. Pretty amazing, don't you think? I have a student in my class who's listening to me rattle on the video. Acid-base reactions. If you mix a solution of a strong acid containing hydronium ions with a solution of a strong base that has an equal number of hydroxide ions, a neutral solution results. The final solution has properties that are characteristic of neither an acid nor a basic solution. Consider these examples. HCl plus NaOH yields NaCl plus water. H2SO4, sulfuric acid, plus 2KOH yields K2SO4, potassium sulfate, plus 2H2O. In each example, a strong acid reacts with a strong base. If solutions of these substances are mixed in the mole ratio specified by the balanced equation, neutral solutions will result. Very important when you talk about buffers. Similar reactions of weak acids and or weak bases do not usually produce neutral solutions. In general, however, reactions in which an acid and a base react in an aqueous solution to produce a salt and water, they're called neutralization reactions. Remember, they're with strong acid and strong bases. The formation of water in a neutralization reaction is shown in figure 20, where you have 1 mole of hydronium plus 1 mole of hydroxide will yield 2 moles of water. Where'd you get the 2 moles from? Well, remember, the hydronium ion is water plus a hydrogen ion. So if I take that hydrogen ion and I put it with the hydroxide, what's left is a water molecule, and then you're making a water molecule. So you're creating a water molecule by taking the hydrogen ion off the water, and then you're creating another one by putting the hydrogen ion on the hydroxide. So you will end up with 2 moles of water. 1 mole of hydronium plus 1 mole of hydroxide is 2 moles of water. Neutralization reactions are one way to prepare pure samples of salts. You could prepare potassium chloride, for example, by mixing equal molar quantities of hydrochloric acid and potassium hydroxide. An aqueous solution of potassium chloride would result. You could heat the solution to evaporate the water, leaving the salt, potassium chloride. On the next page lists some common salts and their application. So let me read that again. You could heat the solution to evaporate the water, leaving the salt, potassium chloride, provided that your calculations were correct and you had 1 mole of the base and 1 mole of the acid. If you have excess one or excess the other, your water will not be pure. You'll have things dissolved in it that are not salts. You'll either have a little excess base or excess acid. And here are some salts and their applications. Fertilizer, gastric juices, antacid. Look at that, photographic emulsions. You studied emulsions in chapter on water and aqueous systems. You have sodium-free salt substitutes, body electrolyte, chlorine manufacture. You have de-icing roadways and sidewalks, etc. So there are a lot of salts. The production of salt is a very big industry because we use salts of all kinds to do a variety of things either around the house or in industry. So salts are important, and it's not just sodium chloride. In general, the reaction of an acid with a base produces water, and one of a class of compounds called salts. When you hear the word salt, you may think of the substance that flavors your French fries or scrambled eggs. Table salt, that's sodium chloride, in one example of a salt. But there are many more. Salts are compounds consisting of an anion from an acid and a cation from a base. That's the definition of a salt. The properties of salts, the properties of acids and bases and salts help explain many diverse phenomena. The usefulness of antacids, for example, depends on the process of acid-base neutralization. Farmers use a similar process to control the pH of soil to grow your food. Titration. Acids and bases sometimes, but not always, react in a 1-to-1 mole ratio. Hydrochloric acid plus sodium hydroxide yields sodium chloride, and water, that's 1-to-1 ratio. When sulfuric acid reacts with sodium hydroxide, however, the ratio is 1-to-2. 2 moles of the base sodium hydroxide are required to neutralize 1 mole of sulfuric acid, because remember, sulfuric acid, H2SO4, is diprotic. So it's going to be H2SO4 plus 2NaOH yields sodium sulfate, that's Na2SO4 plus H2H2O. So it's 1 mole of sulfuric acid, 2 moles of sodium hydroxide, yields 1 mole of sodium sulfate and 2 moles of water. Similarly, hydrochloric acid and calcium hydroxide react in a 2-to-1 ratio. 2HCl plus CaOH2 yields CaCl2 plus 2HOH. Hydrochloric acid plus calcium hydroxide yields calcium chloride plus water. 2 moles of hydrochloric acid plus 1 mole of calcium hydroxide yields 1 mole of calcium chloride and 2 moles of water. You will notice in the preceding examples that the number of moles of hydrogen ions provided by the acid are equivalent to the number of hydroxide ions provided by the base. When an acid and base are mixed, the equivalence point is when the number of moles of hydrogen ions equals the number of moles of hydroxide ions. You can determine the concentration of acid or base in a solution by performing a neutralization reaction. You must use an appropriate acid-base indicator to show when neutralization has occurred. As you can see in figure 21, the juice of red cabbage, the juice of red cabbage is an acid-base indicator. In the laboratory, phenolphthalein is often the preferred indicator for acid-base neutralization reactions. Solutions that contain phenolphthalein turn from colorless to deep pink as the pH of the solution changes from acidic to basic. In slightly basic solutions, the indicator is very faintly pink, but it maintains its pinkness. Here is red cabbage juice is used as an acid-base indicator. This is figure 21. As the solution changes from highly acidic to highly basic, the color changes from red to violet to green to yellow. So you can actually determine with pretty good accuracy the pH of a solution based on its color. Here's another one where you have, again, the red to the green, going from 1 to 12. It's a pretty accurate indicator, even though it's cabbage juice. Figure 22, the titration of an acid with a base is shown here. A known volume of an acid plus a few drops of phenolphthalein indicator in a flask is placed beneath a burette filled with a base of known concentration. B. The base is slowly added from the burette to the acid while a flask is gently swirled. A change in the color of the indicator signals that neutralization has occurred. That's C. And you can see that it's a nice, deep, hearty pink color, and it maintains that pink color. It doesn't fade away. When you drop the solution in A, when it mixes, it finally dissipates, and when it stays there, that's when you know you have a substantial change in the pH indicated by the indicator. The steps in a neutralization reaction are as follows. 1. A measured volume of an acid solution of unknown concentration is added to a flask. 2. Several drops of the indicator are added to the solution while the flask is gently swirled. 3. Measured volumes of the base of known concentration are mixed into the acid until the indicator just barely changes color. The process of adding a known amount of solution of known concentration is to determine the concentration of another solution is called titration. The solution of known concentration is called the standard solution. Use a burette to add the standard solution. A titration is continued until the indicator shows that neutralization has just occurred. The point at which the indicator changes color is the end point of the titration, when it just holds that color. The titration of an acid of known concentration with a standard base is shown in Figure 22. You can use a similar procedure to find the concentration of a base using a standard acid. Figure 23 shows how the pH of a solution changes during the titration of a strong acid with a strong base. The pH of the initial acid solution is low. As the base is added, the pH increases because some of the acid is neutralized. Figure 23, in this titration of a strong acid with a strong base, 0.01 molar NaOH is slowly added from a burette to 50 milliliters of 0.10 molar HCl in the beaker. The equivalence point, the midpoint on the vertical portion of the pH titration curve, occurs at 50 milliliters of NaOH added. Notice they're using an indicator and a pH meter. Interesting. As the titration approaches the point of neutralization at a pH of 7, the pH increases dramatically as hydrogen ions are used up. Once past the point of neutralization, additional base produces a further increase of pH. The point of neutralization is the end point of the titration. At this point, the content of the beaker consists of only water and sodium chloride, which is the salt derived from the strong acid HCl and the strong base NaOH, plus a trace of indicator. Salt hydrolysis. A salt consists of an anion from an acid and a cation from a base. It forms as a result of a neutralization reaction. Although solutions of many salts are neutral, some are acidic while others are basic. Solutions of sodium chloride and potassium sulfate are neutral. A solution of ammonium chloride is acidic. A solution of sodium ethanoate, sodium acetate, is basic. Figure 24 shows a titration curve obtained by adding a solution of sodium hydroxide, a strong base, to a solution of ethanoic acetic acid, a weak acid. An aqueous solution of sodium ethanoate exists at the equivalence point. Here is acetic acid plus sodium hydroxide yields water plus the acetate ion, or ethanate. The pH of the equivalence point is 8.7, and that is basic. You can see that it's not 7. So it would be 7 if it were a sodium chloride and salt. It would be neutral, which is from hydrochloric acid and sodium hydroxide. This is going to lead right into the concept of buffers. So I want you to look this over, salt hydrolysis, several times in order to understand buffers, which is one of the more difficult aspects of all of chemistry. The titration curve for a weak acid and a strong base is compared with the titration curve for a strong acid and a strong base. So here you see the difference. This is figure 24. Look this over and you can see that there is acid left over, the acetic acid, and the anion to acetic acid, acetate or ethanoate, sometimes just simply pronounced ethanate, ethanoate, as ethanate, ethanoate, ethanoate. So it's a difficult word to pronounce, but hang in there. It's not that bad. For a strong acid, strong base titration, the pH at the equivalence point is 7 or neutral. The difference exists because some salts promote hydrolysis. In salt hydrolysis, the cations or anions of a dissociated salt remove hydrogen ions from or donate hydrogen ions to water. Depending on the direction of the hydrogen ion transfer, solutions containing hydrolyzing salts may either be acidic or basic. Hydrolyzing salts are usually derived from strong acid and a weak base, or from a weak acid and a strong base. Sodium carbonate, washing soda, is the salt of a strong base, sodium hydroxide, and carbonic acid, a weak acid. Ammonium nitrate, used in fertilizers, is a salt of a weak base, ammonia, and nitric acid, which is a very strong acid. Vapors of the strong acid, HCl, and the weak base, ammonia, combine to form the acidic white salt, ammonium chloride, NH4Cl, ammonium chloride, and it's a white vapor. And it's actually used in a demonstration of Graham's law of effusion. Soap is a salt of a strong base, usually sodium hydroxide, and stearic acid, a weak acid present in fats. In general, salts that produce acidic solutions contain positive ions that release protons to water. Salts that produce basic solutions contain negative ions that attract protons from water. Sodium, I refuse to say ethanoate, we're going to call that sodium acetate, is the salt of a weak acid, ethanoic acid or acetic acid, and a strong base, sodium hydroxide or NaOH. In solution, the salt is completely ionized. Acetic acid yields the acetate ion plus the sodium ion. Now, this is going to be a very important reaction because the acetate ion is going to combine with water, and it's going to steal a hydrogen from water, producing hydroxide, as you'll see in a moment. So very, very important reaction relative to the buildup to buffers. The acetate ion is a Bronsted-Lowry base, which means it is a hydrogen ion acceptor. It establishes an equilibrium with water, forming electrically neutral ethanoic acid, acetic acid, and negative hydroxide ions. So the acetate ion plus water yields acetic acid plus the hydroxide ion. This process is called hydrolysis because it splits a hydrogen ion off a water molecule. The resulting solution contains a hydroxide ion concentration greater than the hydrogen ion concentration. Thus, the solution is basic. So if you're trying to find out what the pHs of the solution, you have to use a Kb because you're producing hydroxide. So the Kb expression is what you're going to use. Ammonium chloride, NH4Cl, is the salt of a strong acid, hydrochloric acid, HCl, and a weak base, ammonia, NH3. It is completely ionized in solution, and there's the reaction. Figure 26, a few drops of universal indicator solution have been added to each of these 0.1 molar aqueous salt solutions. The color of the indicator shows the following. A. Ammonium chloride, NH4Cl, is acidic, pH of approximately 5.3. Sodium chloride is neutral, pH 7. Sodium acetate is basic, pH about 8.7. So you see it goes from yellow to green to blue. So you would have to use an indicator that has that range. If you're going to show 3 different variations, you should be using the same indicator. So you need an indicator that's going to go from 5.3 to 8.7. The ammonium ion, NH4 plus 1, is a strong enough acid to donate a hydrogen ion to a water molecule, although the equilibrium is strongly to the left. NH4 plus water yields NH3 ammonia plus hydronium ion concentration. The ammonium ion is a hydrogen ion donator, Braunsted-Lowry acid. The water is a hydrogen ion acceptor, Braunsted-Lowry base, and it's going to make the solution acidic. So if you have a salt such as ammonium chloride, that solution that's formed by putting the ammonium chloride in water will be acidic because the ammonium ion is a Braunsted-Lowry acid. This process is also called hydrolysis. It results in the formation of ammonia molecules and hydronium hydrogen ions. The hydronium ion, molar hydronium ion concentration is greater than the hydroxide concentration. Thus, a solution of ammonium chloride is acidic. To determine if a salt solution is acidic or basic, remember the following rules. Strong acid plus strong base yields neutral solution. Strong acid plus weak base is equilibrium. It reaches an equilibrium, and it's generally going to be acidic solution. Not very strong, but it's still going to be acidic solution. A weak acid and a strong base is going to be a basic solution, and it's going to be in equilibrium. The addition of 10 milliliters of 0.10 molar sodium hydroxide to 1 liter of pure water increases the pH by 4 pH units from 7 to 11. A solution containing 0.2 moles per liter or 0.2 molar each of ethanoic acid and sodium acetate has a pH of 4.76. When moderate amounts of either acid or base are added to this solution, however, the pH changes little. The addition of 10 milliliters of 0.1 molar sodium hydroxide to 1 liter of this solution, for example, increases the pH by only 0.01 pH unit, from 4.76 to 4.77. Figure 27 shows what happens when 1 milliliter of 0.01 molar HCl solution is added to an unbuffered solution. The solution of ethanoic or acetic acid and sodium acetate is an example of a typical buffer. We will get into buffer systems, the week after next. Figure 27, a buffer is a solution in which the pH remains relatively constant. A. The indicator shows that the buffered solution on the left and the unbuffered solution on the right are basic, about pH 8. B. After the addition of 1 milliliter of 0.01 molar HCl solution, the pH of the buffered solution shows no visible change, yet the pH of the unbuffered solution is now about 3, and the solution is acidic. So a buffer will maintain the integrity of the pH of a system. A buffer is a solution in which the pH remains relatively constant or stable when small amounts of acid or base are added. A buffer is a solution of a weak acid and one of its salts, or a solution of a weak base and one of its salts. A buffer solution is better able to resist drastic changes in pH than is pure water. Buffer comes from the Old English word buff, meaning firmly or sturdily. A buffer solution resists change in its pH even when acidic or basic solutions are added to it. What does it mean if authorities set up a buffer zone around a fire investigation site? So the word buffer is synonymous with stability or integrity against change. Figure 28, 2 pages from now, illustrates how a buffer works. Ethanoic acid and its anion, acetate, act as reservoirs of neutralizing power. They react with any hydroxide ions or hydrogen ions added to the solution. For example, consider the buffer solution in which the sodium acetate is completely ionized. So you start with acetic acid, and then you start with sodium acetate, and you have that completely ionized, completely dissociated into the acetate ion and the sodium ion. So it is completely ionized. Now what? Your body functions, this is blood buffers, this is kind of an on the side. Your body functions properly only when the pH of your blood is between 7.35 and 7.45. A blood pH outside these narrow limits can be life-threatening. To keep your blood at the proper pH, your blood contains buffers. The most important blood buffer consists of carbonic acid and hydrogen carbonate ions, or bicarbonate ions. Hydrogen ions produced by chemical reactions in your body are the main threat to your blood's pH. This buffer maintains the desired blood pH by removing excess hydrogen ions. As long as there are hydrogen carbonate ions available, the excess hydrogen ions are removed, and the pH of the blood changes very little. Here is figure 28, which shows how a buffer works by maintaining the integrity of the pH of a system, such as this buffer system. Figure 28, the buffer described here is made of ethanoic acid and sodium acetate, which is the source of acetate ions. To begin, the concentration of ethanoic acid and acetate ions are equal. When neither H plus or OH minus is added, the buffer produces additional ethanoic acid or acetate ions. In both situations, the ratio of acetic acid concentration to acetate concentration, and consequently the pH changes very little. Here's another shot of figure 28. The left reaction is acid is being added, and in the right reaction, OH is being added. When an acid is added to the solution, remember we were producing the acetate ion, that was the first reaction, sodium acetate. When an acid is added to the solution, the acetate ions, CH3COO -1, act as a hydrogen ion sponge. This creates ethanoic acid, which does not ionize extensively in water. Thus, the pH does not change appreciably. So the acetate ion plus water yields acetic acid plus the hydroxide ion. The base is a source of hydroxide ions. When a base is added to the solution, the ethanoic acid and the hydroxide ions react to produce water and acetate ion. Acetic acid plus sodium hydroxide produce water plus the acetate ion. Now don't forget, let's be clear, ethanoic acid is acetic acid. Ethanoate is acetate. So don't let me confuse you, although it certainly sounds like I am, but it's been changed over recent years that ethanoate is commonly referred to in some texts as acetic acid and vice versa. Here are the 4 reactions that summarize what we've been doing for the buffer system of acetic acid and the acetate ion. Notice I am not saying ethanoic acid or ethanoate. Just keep it simple. So you have acetic acid plus sodium hydroxide yields water plus the acetate ion. You have acetic acid plus water yields the hydrogen ion or the hydronium ion plus the acetate ion. And then you have sodium acetate yields the acetate ion plus sodium ion. And then you have the acetate ion plus water yields acetic acid plus the hydroxide ion. That summarizes all the equations we've been using relative to ethanoic acid, etc. The acetate ion is not a strong enough base to accept hydrogen ions from water extensively. Again, the pH does not change very much. An acetate buffer solution cannot control the pH when too much acid is added, because no more acetate ions are present to accept hydrogen ions. The acetate buffer also becomes ineffective when too much base is added. Do you know why this is so? When too much base is added, no more ethanoic acid molecules are present to donate hydrogen ions. When too much acid or base is added, the buffer capacity of a solution is exceeded. The buffer capacity is the amount of acid or base that can be added to a buffer solution before a significant change in pH occurs. 2 buffer systems are crucial in maintaining human blood pH within a very narrow range. That's pH 7.35 to 7.45. One is the carbonic acid hydrogen carbonate buffer system. The other is the dihydrogen phosphate monohydrogen phosphate buffer system. Table 10 lists several important buffer systems. You have the acetic acid acetate ion system, and you also have the 2 that we just mentioned, and also the ammonium ion ammonia buffer system. And that concludes the lecture for acid-base chemistry chapter.